Welcome to week 8, day 1 of distance learning. Students, you do not need the pre-printed note sheet for today's notes. You can easily copy the notes directly into your notebook or journal or on a sheet of notebook paper. You can also pause the video at any time to copy notes or work examples. Today we will graph rational functions. But what is a rational function? Take a couple minutes to read through the questions and see if you can answer them on your own. When you look at the word rational, the mini word that you might see in there is ratio. And we know that a ratio is a comparison of two numbers by division. The numbers a and b are always going to be integers, but b cannot equal 0. If b were equal to 0, then our expression would be undefined. So what does the term rational mean in terms of mathematics? It means we're going to have algebraic expressions that involve a fraction a over b. Based on this, we can assume that rational functions will involve fractions, and the independent variable x will always be in the denominator of the fraction. So what might a rational function look like? F of x equals 1 over x is a rational function, and f of x equals 1 over x squared is also a rational function. These are the two parent rational functions that we will be studying in this unit. The first rational function that we will study is f of x equals 1 over x. Go ahead and make a t-table in your notes, and then spend a few minutes to see if you can evaluate the function f of x equals 1 over x for these values of x. So remember, you're going to substitute -3 for the x, you'll have 1 over -3, which will be -1/3. So go ahead and pause your video, make the table, and spend a few minutes filling in all the y values for the x values that I've given you. Hopefully you've found the same values for y that I have. And if you make a quick sketch of these, what will it look like? It's going to look like this with two curves. One curve is in the first quadrant and one curve is in the third quadrant. Notice that we have no graph at the origin, and the function is undefined where x equals 0. I've added some more information to our parent graph of f of x equals 1 over x. We know when we look at the function and it's getting closer and closer to this axis here, and it's also getting closer and closer to the horizontal axis going in this direction, we know that these axes are then asymptotes. In this parent function, the horizontal asymptote will be y equals 0, which is drawn with a dashed green line, and the vertical asymptote is drawn also with a green dashed line, x equals 0. Where the two asymptotes cross, that's what we're going to refer to as our HK point. And notice how the HK point, and in this case 0, 0 for the parent function, it is not on either of the curves. But we do use this HK point as a reference point. When we draw our functions, our rational functions, we're always going to sketch our curves, and they don't have to be exact because we're dealing with all these fractions and these numbers here. So the curves don't have to be exact, but we always want to mark the HK point with a little x, and then we want to go ahead and get these 2 points. And if you look at our table of values, the points I'm talking about are 1, 1, and -1, -1. Notice, to go from the HK point to this 1, 1, it's 1 to the right and 1 up. And going to the -1, -1, it's 1 to the left and 1 down. So all of our rational function graphs, we should see the curves and these 2 points marked, as well as the HK. So summarizing the information, we have our table of values, we have our important points, -1, -1, the HK point, which we indicate with an X, and the other point, 1, 1. Horizontal asymptote, y equals 0, vertical asymptote, x equals 0, and then our domain. Our domain is defined for all values of x except for 0. So since we have two curves, we have two parts to our domain, -infinity to 0, union 0 to infinity. Likewise with the range. The range, we have two parts as well. Negative infinity to 0, union 0 to infinity. So this is our parent function, f of x equals 1 over x. Our second parent function is f of x equals 1 over x squared. Take a few moments to see if you can complete the table of values, make an approximate sketch, and identify the two important points as well as the HK. Hopefully your table of values matches mine. And when you make your sketch, you notice that this graph also has two parts, but they're in the first quadrant and the second quadrant. And the sketches seem to be going in the same direction. We still have a horizontal asymptote at y equals 0. And we have a vertical asymptote at x equals 0. Remember, the asymptote is the line that the graphs approach as they go towards 0, but they never touch. We have our HK, which is where the two asymptotes cross, and in this case, for the parent function, the HK is 0, 0. Notice how neither of the curves for this function touch the HK point. We still have these two important points that we're going to graph on each of our graphs that we make. One is 1, 1. So from the HK, it's 1 to the right and 1 up, as long as A equals 1. And the other point is negative 1, 1. So 1 to the left and up 1. This function is similar to a quadratic or an absolute value function in that we have no negative values for y. So we see that when we look at our range as well. Notice how our range is only from 0 to infinity because we have no negative values for y. Our domain has two parts, from negative infinity up to 0 and from 0 to infinity. So whenever we're graphing a parent function, 1 over x squared, or make transformations with the function 1 over x squared, the general shape will look like this. There'll be two parts, and both of the parts of the function go in the same direction. Let's take a moment to see what the transformations for these rational functions will look like. The rules for the parameter changes for rational functions are the same as the rules for the other functions we have studied. The parent function y equals 1 over x in transformation form looks like f of x equals y, either 1, equals a over x minus h plus k. The parent function y equals 1 over x squared in transformation form will be f of x or y equals a over x minus h squared plus k. As with the other functions that we studied, the h is a horizontal translation. And remember, insiders lie. So it's x minus h. So this sign will actually be the opposite of what you think. A is the vertical dilation factor, and a negative a represents a vertical reflection, which is when you reflect over the x-axis. The k is the vertical translation, up and down. When we're working with our rational functions, we remember that we have two asymptotes. Our horizontal asymptote will always be y equals a, and our vertical asymptote will be x equals h. When we're working with rational functions, remember the hk point is not on the curve of the graph, but we use the hk point for reference. When we have a function y equals 1 over x for the parent function, remember we have 2 points that we're looking at, both from the hk point. So if a were 1, then we would go to the right 1, up 1 to get the first point, and go to the left 1, down 1 for the second point. If our parent function is y equals 1 over x squared, again we work from the hk point. If a equals 1, we go right 1, up 1 for the first point, and then we would go left 1, up 1 for the second point. Let's go ahead and try a couple examples. We would like to graph the function y equals negative 1 over x minus 1 plus 3. So I gave you some hints here to try and graph this function or make a sketch of the function. You first want to identify which the parent function is, identify your horizontal and vertical asymptotes, your A value and what it means, identify your HK, and then the 2 points that we take as a reference from the HK when we consider the A value. And lastly, you want the domain and the range. Go ahead and pause the video and give yourselves a chance to try this. You notice that the parent function will be 1 over x, and the parent function normally would be in the first and the third quadrant. Looking at our function here, we notice that this is our k value, so we know that our horizontal asymptote will always be y equals k. So here it is drawn on my graph in green, horizontal asymptote, y equals 3. The vertical asymptote is always the x equals h, so x minus 1, so h equals 1. So my vertical asymptote is x equals 1. So here's my vertical asymptote drawn in. And we're just estimating where these lines are. We see that our A value is -1. So that means we're going to be reflecting vertically. So we're reflecting over the x-axis, over the horizontal asymptote of y equals 3. So we start with our HK point, and our HK point is 1, 3. You can see it here with the orange X. So now we need to figure out where our 2 exact points are going to be. And when we have a function that's 1 over x, we normally go 1, 1 to get one of the points from HK, and the other point is -1, -1 from the HK. But notice since our A value is -1, we always multiply the Y values by A, so I'm going to multiply these Y values by -1. So now I need to go to my new point, 1, -1. So if I'm starting at 1, 3, 1, -1 would be 1 to the right and then 1 down. So again, I'm starting at my HK point, which is 1, 3. My new point will be 1, -1. So I'm going to go 1 to the right in the X direction and 1 down in the Y direction. So starting at 1, 3, go 1 to the right and down 1. You also can just look at adding these numbers together. 1 plus 1 is 2, and 3 minus 1 is 2. Let's look at our second point. Our second point is normally -1, -1 from the HK value. But in this case, again, since A is -1, we multiply the Y values by -1. So now it's going to be -1 plus 1. So starting at my HK value, the -1 says move to the left 1, and the +1 in the Y direction means to move up 1. So our point here will be 0, 4. Again, you can look at adding the coordinates. 1 minus 1 is 0, and 3 plus 1 is 4. So here we have a sketch of our function, y equals -1 over x minus 1 plus 3. And you can see that our domain will be all the values from from -infinity to 1, union 1 to infinity. Notice that the function is not defined when x equals 1, because if I put a 1 in here, 1 minus 1 would be 0, and then my function would be undefined. So that's where my vertical asymptote is. And then my range will go from -infinity to 3, and then from 3 to infinity. So take a moment to go through this again, make sure you understand all the steps, and then we'll move on to the next example. Our next example that we're going to sketch the graph for is y equals 2 over x plus 3 squared plus 5. So you see where we have the x plus 3 squared, that tells us that our parent function is going to be 1 over x squared. And remember the parent function with 1 over x squared, the points from the HK are 1, 1, and -1, +1. So take a few moments to see if you can graph this on your own. You want to make sure you're answering all these questions here as you go through making your sketch. As we mentioned before, the parent function is y equals 1 over x squared. And with this parent function, we notice that both parts of the curve go in the same direction. We want to identify our horizontal asymptote. Our horizontal asymptote is always y equals k. So our horizontal asymptote is y equals 5. Sketching it on the graph with a dashed line, and we also want to label it. Our vertical asymptote will be h. So x plus 3 is the same as x minus negative 3. So h equals negative 3. So our vertical asymptote will be x equals negative 3. Again, I've sketched it on the graph here in green. Looking at our function, we see that our a value is 2. That tells us that our function is going to stretch vertically. We don't have any reflecting, but we do have a vertical stretch. So when we plot our HK point is negative 3, 5, and I've marked it here with an X. And what do we know about our points? Our points would be 1, 1 if A were equal to 1, and negative 1, 1 if A were equal to 1. So I've added here some explanation of what happens when our A value is equal to 2. We know that the A value is always multiplied by y. So from the HK point for this type of function, we would normally go 1, 1 and negative 1, positive 1. But since we're multiplying the y values by 2, instead of going 1, 1, we're going to go 1, 2. So starting at negative 3, 5, I'm going to go 1 in the x direction, and I'm going to go 2 in the y direction. So that tells me my exact point here will be negative 2, 7. Working with the negative 1, positive 1, again, I multiply this y value by 2. So starting from HK, I'm going to go to the left 1 and up 2, and that'll take me to negative 4, 7. So that's my second exact point. Again, we can add these. Negative 3 plus 1 equals negative 2. 5 plus 2 equals 7. For the second point, negative 3 minus 1 is negative 4, and 5 plus 2 equals 7. So we can see with our function, where the parent function is 1 over x squared, both sides of our curve go in the same direction, and we're not touching our asymptotes. What is our domain? Well, our domain goes from negative infinity to negative 3, union negative 3 to an infinity. Remember, if I put a negative 3 here, what's going to happen? I'm going to have a 0 in the denominator of the fraction, and that is undefined. So that corresponds with our vertical asymptote. And then we notice with our range is all above the horizontal asymptote, so our range will be from 5 to infinity. Take a moment to make sure you understand all of our graphing for this problem, and then we'll go ahead and move on. Our next two examples, I'm going to give you the sketch of a graph for a rational function, and you're going to write the equations. So notice you can read the asymptotes, the horizontal asymptote and the vertical asymptote, and you have these two exact points. So your strategy for writing the equation will be the first step is to figure out which parent function this is. Is this 1 over x or 1 over x squared? Notice how we're opposite here, we're cross. So that's a hint that we're going to have a parent function of y equals 1 over x. Then you have your h and your k values that you can read from the asymptote. You can mark your hk value and then see if you can work backwards to figure out what your a value is going to be. So take a few moments to see if you can figure it out on your own, and then go ahead and move on with the video. We see that the parent function is y equals 1 over x because the two parts of the curve are opposite of each other and they're not going in the same direction. So in transformation form, our equation should look like y equals a over x minus h plus k. We need to identify what the h and the k are, and we know the h is always going to be the vertical asymptote. So my vertical asymptote is here, x equals 2, so that tells me that my h value is 2. The horizontal asymptote is always y equals k, so that tells me that my k value is going to equal 3. Once I have hk, I can graph my hk point in the middle, hk, and I can use that to figure out what the a value is. We know that if the a value were 1, I'd go to the right 1 and up 1, but it looks like I'm going to the right one and up 3. So since I'm going to the right one and up 3, and then to the left one and down 3, that tells me that my A value is going to equal 3. I can also look here. 6 minus 3 is 3. 3 minus 0 is 3. So you're just comparing the y values. Again, 6 minus 3 in the y's tells me my A value is 3. And then from here to the point on the left, 3 minus 0 is 3. So I know that my A value is equal to 3. So my function will be y equals 3 over x minus 2 plus 3. Let's try one more. By looking at this graph, you can immediately tell that the parent function is y equals 1 over x squared. And you probably noticed right away that instead of the function going up, both of them are going down. So that's going to tell you that it's reflected over the x-axis. So your A value is going to be negative. Take a few moments to see if you can go through the steps that we did on the last example, and if you can write the equation for this rational function. So our parent function is y equals 1 over x squared, which means transformation form will be y equals a over x minus h squared plus k. Again, we get our h value from our vertical asymptote. So we know that h equals 7, and we get our k value from our horizontal asymptote, so k equals negative 4. So we know 7, negative 4 is our hk value, and then we just need to figure out what a is. So I look at the coordinates for these points. I'm at 7, negative 4, and my new point is 8, negative 5. So what do I have to do from negative 4 to get to negative 5? I'm just going to subtract 1. So there's my clue that the a is going to be a negative 1. Notice that the 6, negative 5 and the 8, negative 5 both have the same y value. So it's only one difference that we have to look at. So negative 4 minus 1 gives me negative 5. So this would be 1 to the right and 1 down. Also 1 to the left and 1 down. So a equals negative 1, reflected over the x-axis. So my equation for my function will be y equals negative 1 over x minus 7 quantity squared minus 4. Please copy the following practice problems to try on your own. For each function, you want to identify the parent function, describe the parameter changes from the parent function, identify and sketch and label the asymptotes, sketch the curves and approximate and label the 2 exact points on each graph, and write the domain and range for each in interval notation. Good luck.